To begin with, I would like to thank the organizer and especially Professor Prashant Panigrahi, with our long-term friend and collaborator, for organizing this meeting. And I'm sorry for the inconvenience caused from my end. There was a meeting and I had to shift my talk. And I'm extremely thankful for the organizer for showing the great flexibility and shifting it. So I'll talk about quantum communication beyond conjugate coding-based point-to-point quantum key distribution. So in the slide, there is a picture. And in the picture, you can see that there is a point-to-point communication happening. There is a one point is at China, one point is Austria. But this is between 2 points. And most of the time, or the easiest protocol to understand is a conjugate coding-based protocol. So we'll come to that, what is conjugate coding-based protocol, and I'll describe that and some other protocols also, that which is not conjugate coding, and I'll keep describing that. Apart from point-to-point key distribution, quantum cryptography had many facets. So something we have written on this slide also. So you can see that the slide is divided into 3 pieces. So in the left-hand piece, I write single photon and entangled photon source, efficient single photon detector, quantum memory, quantum repeater, etc. So what are these? So these are technological challenges where quantum mechanics does not stop you from making a good quality single photon source or a very efficient single photon detector, but we don't have it in the market. So we need commercially available efficient single photon detectors for all wavelengths. So this is an engineering challenge. We need quantum memory, we need quantum repeater, and in the National Quantum Mission there are projects, and in other places also people are trying to build this. So left-hand side makes a list of engineering challenges. And if you want to do research in that, that's not essentially a point-to-point QKD. It's beyond that. It's actually making peripheral technology which will boost the quantum cryptography. In the right-hand side, we write something called TFQKD. This stands for twin field quantum key distribution, measurement device independent quantum key distribution. These are state of art. So quantum key distribution, I'll not be able to describe all such protocol, but I'm just giving a brief idea about what's happening on the world. So twin field quantum key distribution gives you the highest possible length at the moment. So at the moment, we can go up to 1200 kilometer, and in twin field QKD, there is a center node where we do measurement, and each arm can be 600 kilometer or so. So why it's interesting? Because as I mentioned that there is no repeater. So in absence of the repeater, signal gradually become weak. And then since you don't have a repeater, you cannot, either you have a trusted node or you cannot increase the distance. So twin field QKD is very interesting at the moment, and it can beat certain limit also. It has the flavor of measurement device independent quantum key distribution. So what is measurement device independent quantum key distribution? So in what follows, we'll discuss that quantum cryptography is unconditionally secure, but it's not unhackable. So what does it mean? So classical cryptography is conditioned. The security comes from the complexity of the mathematical problems. For every cryptographic scheme, correspondingly in classical world, there is a mathematical problem, and we don't have an algorithm to solve it in reasonable time. So suppose my algorithm takes it, the best algorithm with the best computer takes 1 hour to solve it. And I want to make it safe for 1 minute, so it is quite safe that nobody will be able to solve it in 1 minute. So this is conditions on somebody's power to solve it. Quantum cryptography is unconditional but not unhackable. So how we hack? Here we exploit device imperfection. So imperfections of the device are used to hack. But now MDI QKD allows you that even if the measurement devices are erroneous or faulty, still you will not be able to hack, or adversary will not be able to hack. But it does not mean that you cannot now hack from the source side. So this is the best thing which you can do at the moment, MDI QKD. Then there is something called semi QKD. So this is semi quantum. Here all the users are not classical. Sorry, all the users are not with full quantum capability. Some of them are classical in the sense, given a quantum state, it can do a measurement in 0-1 basis or reflect it. So I will describe a conjugate coding based scheme of this. And then there is various discrete variable, continuous variable, and DPR protocol. So DPR is largely people put it in DV, but often it is seen slightly different. And then quantum cryptography is not restricted just distribution of the key. There is something called quantum key agreement, quantum secure direct communication, where we don't produce a key, rather I use, without producing a key, we can do a direct communication. There is something called quantum dialogue, which allows us that Alice and Bob both can talk each other without prior generation of the key. And often this is called quantum telephone and such thing. And I would like to mention that long back, Professor Panigrahi and I did a work on asymmetric quantum dialogue. So what asymmetric quantum dialogue means, it's just like this conference. So I will speak more, you will speak less. So then you have a question, you will speak, but most of the time I will speak. So one among Alice and Bob, one needs bigger portion of the channel who speaks more, but it's a dialogue. So it is allowed that the other party can also talk, but the resources given for speaking to the other person is less. Anyway, so let's move. So this is India map and where we are located. I'm located somewhere near Delhi. It's called Noida. This is our campus. And one of these buildings, so the extreme right bottom building, I have a lab. And the lab is called Quantum Technology Lab, Quantum Cryptography Lab. And Quantum Cryptography Lab, we have this kind of thing. So in quantum cryptography, always it happens that, or in quantum communication, that Alice sends and Bob receives. So receiver is Bob, Alice is sender, and there is a eavesdropper, a bad person who tries to eavesdrop. And eavesdropper is in the middle. So now we have everything in a lab. So it's in the same table and there is a tray. So this rack-like structure has all the electronics. Between Alice and Bob looks like computer, and in between there are 120 kilometers of optical fiber. So my Alice and Bob is sitting side by side, but they are separated by 120 kilometers of optical fiber. And this boxes, each of this box has a spool of 40 kilometers of optical fiber. And here we are showing that we generated a key by using something called coherent one-way protocol and their rate, etc. Now we move to, first you feel that why should you do quantum cryptography, or let's understand classical security first to develop a feeling. So a real life example. So if you just put sbicard.com in your mobile phone or your computer, you will see that a lock-like structure is coming in the left. So that means this is secure. So click here. So once you click here, there will become that connection is secure. But I want to quantify how much secure it is. So I click on the click here again, and then it comes more information. Click more information, and you will see a list. And you will find that many of our banks are vulnerable if there is a scalable quantum computer is there, and it's vulnerable for some other reasons too. So a few years back, we did a study on vulnerability of Indian bank, but different legalities stopped us from writing everything. So we wrote only those things which we can safely write in public domain. But anyway, so when you click there, you will see that the detail of the security will come, that who has given the certificate, etc. And you see that connection is encrypted. So my mouse is in a line, connection is encrypted, TLS, ECDHE, RSA with AES, etc. So what are those things? So TLS is a handshake protocol. ECDHE is a combination of two mathematical problems. EC stands for elliptic curve, DH stands for Diffie-Hellman encryption. So for elliptic curve to hack it, we have to develop a protocol which can solve elliptic curve problems in infinite time or short time. So what do we mean by efficient algorithm? We are coming to that. DH stands for Diffie-Hellman. Corresponding mathematical problem is discrete logarithm problem, and RSA stands for a protocol for which the corresponding mathematical problem is factorization of odd biprime, which are not square. If it is a square, you can find out the square root easily. But if I take two large prime number and multiply and give it to you, factorization is a very difficult problem. Now, all these things, elliptic curve, Diffie-Hellman, RSA, all the corresponding mathematical problems are solvable if you have a quantum computer. So for RSA and Diffie-Hellman, Shor provide algorithm. So using Shor's algorithm, you can solve this problem. elliptic. So if you have a quantum computer, you can solve this. So now everybody, and then it is hackable. So it is actually weak for many sense. All bank now use 120 to 256 bit. It is still using 128 bit. Further, TLS 1.2 is not the state of art, and because some of the users still have old phone, so although it is certified at TLS 1.2, it also allows TLS 1.1. So these are vulnerabilities. But we are interested to understand what gives security. So security comes from difficulty of computational problem. Now, how do you quantify that difficulty? So for that, you have to understand this. So suppose, so I often, in every lecture of mine, I start with this and I tell people that, okay, algorithm has nothing to do with computer, and probably the first algorithm that you know was taught by your mother. So we were in the childhood, we were learned that how to do add. So what is algorithm? A systematic procedure to solve a problem. So now you look at this. So suppose I have been asked to add 31 plus 12. So just take the rightmost two digits. So we have been taught that unit place below unit place, 10 place below 10 place, and then add. So if there are two digit, 1 plus 2 is 3, 3 plus 1 is 4, it involves 2 steps. If 3 is digit, it involves 3 steps. 4 digit involves 4 steps. So if there are n digits, it involves n steps. So n digit is the size of the problem. And if n is the size of the problem, how my algorithm or the systematic procedure to solve this problem, in this case addition, it involves how many steps? If it is involved n steps, so we say that it can be solved in n steps. Now you see multiplication. So adding 12 plus 34 will involve 2 steps. But if you do multiplication, you have to do 2 into 4, 1 into 4, 2 into 3, 1 into 3. Then you have to do 3 additions. So it involves 7 steps. So at least we learn that multiplication is more complex than addition. So how we calculate complexity? So if n is the size of the problem, how many steps is needed to solve the problem? So if it is n square, n cube, n to the power 4, or any polynomial of n, all such problems form a family, and I say that these problems are solvable in polynomial time. So they belong to a family called P. Now, if you can solve in polynomial time using quantum resources, that will be called Q. So P is a classical class. So it has all the problems for which I have a systematic procedure to solve in polynomial system. So here I would mention that if you can do it in log n, root n, which are shorter than the polynomial n, they also belong to this polynomial class. So if I can solve it in this way, then we have an efficient solution for this. But now the belief is that there are problems for which the solution can be checked in polynomial time. So I give you a factor, there is a large number, and I tell that large number is n, capital N, and P is its factor. You will divide and check that P is a factor or not. So solution can be checked in polynomial step, but the problem is not essentially solvable in polynomial number of steps. So all the problems for which solution can be checked in polynomial steps belong to NP. So you see this yellow block. So NP is expected to be bigger than P, because P has the problem which can be solved in polynomial time, and NP is the problem for which solution can be checked in polynomial time. But whether P is a proper subset of NP or not, that nobody knows. But computer science is more like a religion where there are many beliefs, and the belief is that P is not equal to NP and P is a subset of NP. Now, there are problems which you can solve probabilistically, not deterministically, in polynomial number of steps. So they belong to a class. So P is solved deterministically. There is a bigger class called BPP, which is not shown here. So that's a classical class that classically you can solve these problems. Yeah. Now, in polynomial number of steps, but probabilistically. Then comes that if you use quantum resources and solve a problem probabilistically, but the error is bounded. So my algorithm will sometimes succeed, sometimes fail. But when it fail, then I know, and I can bound the failure rate. So I can bound it like 10% of the time it will fail, 15% of the time it will fail, or 1% time it will fail. That will depend. That will decide my number of iteration. So BQP stands for all such problems for which quantum, if you use quantum resources, you can solve them in polynomial time, but with bounded error. So these are probabilistic algorithms. So at the moment, the belief is that quantum computer can only solve BQP problem from BQP complexity class, and BQP is a subset of NP. So there are problems in NP which is outside. So now you can see that BQP is solving problems outside P but in NP. So integer factorization, discrete logarithm, etc. are there. So if a problem, complexity, a computational problem was fetched from this, then that is vulnerable. But now if there are problems which is in NP but outside BQP, and you take a problem from that and create a cryptographic scheme, still classical, still conditional, so it will be considered to be quantum safe. But it is quantum safe under severe assumptions. The assumption that quantum computer cannot solve BQP problems outside BQP. BQP is a subclass of NP. P is a subclass of NP. So if these assumptions of computer science are true, and then you develop something, then this will be cryptographically quantum safe. And such classical algorithms are now called PQC, post-quantum cryptography. Post-quantum cryptography means post is after a scalable quantum computer is built, still it is safe, which is not the case to is RSA or Diffie-Hellman or electric car. So, but at the moment, this will still remain conditional. Now, so that's the notion. So classically, nothing is unconditionally secure, quantum mechanically, and we talked about complexity, so this is important. And here, one point to understand. So here is a cartoon that a student did very bad, he got F-grade, and he went to his teacher, and teacher told that, why you have not answered anything? He told that, okay, in exam, all the problems were in NP. So I could not solve them in 3 hours of exam. So now, you see, teacher is telling that if you don't give effort, then things may appear in NP. So now, extending this, we may tell that sometimes people thought that discrete logarithm or odd biprime factorization cannot also be solved in polynomial time. But with the development of quantum algorithms, we have seen that they are solvable. So the same maybe happen with all the other problems which are outside P and not yet solved by quantum algorithm. So more efforts are needed and before believing that PQC is actually safe. But PQC does not require, post-quantum cryptography does not require any additional resources. So we often use that. Now, while we talk about algorithm, how to find out its complexity, we can find out it always in the worst case, not in the best case. So Grover's algorithm is an interesting algorithm to explain that. So Grover's algorithm stands for unsorted database search, and the popular example is a telephone directory where the numbers are organized as per the names. And now you give a randomly one number and ask you to find out what is its name. So if there are n data, sometime you may take n searches, sometime you will do it in fast searches by CODE method, and then on an average you need of the order of n searches. Now a teacher asked a student and a student told, I'll just take my mobile, call that number and ask his name. So, but that person may or may not answer, and that's not the best, that's the best case scenario. So complexity is always calculated in the worst case scenario. Okay. So as I mentioned that quantum algorithm, but there are many things that believe in classical cryptography, and we just increase the size of the problem to make our algorithm, make our protocol safe for longer period. But the faster way quantum computers is developing, it's not expected to remain safe for long. And few weeks back, 2-3 weeks back, there was a news that 22-bit RSA is broken. So nobody is using 22-bit RSA. But the news is interesting because the way quantum computers are progressing, soon we'll be able to break probably 128-bit and then 256-bit. And this strategy of increasing the bit size will not work forever, because now what I want to mention that classically the complexity of odd biprime factorization is written here, and here you see that there is an exponential factor. So anything in exponent grows fast, but whereas in quantum it is of the order of log n cube. So it is pretty fast, but then you should ask that why it's not, why the SBI security is not broken so far. The problem is that for factorization algorithm to implement, you need source. If you want to implement source algorithm, you need a very big register. So there is a parallel research to reduce the register size and factorize large number. And Professor Panigrahi has a paper in which it's claimed that a number greater than 90 lakh is factorized using IBM quantum computer. We wrote a paper, we just factorized 35, but we use only one qubit. And these are the progress. So one side is that the requirement of the register size is reducing, and the other side is the quantum computer is also increasing in size. But still the noise is the problem, and we are not in a situation to break 128-bit or so. So that was the present status of classical cryptography and its interaction with quantum computers. But how it all started? It all started more than 50 years ago. In 1970, Stephen Weisner, who was a classmate of Bennett, used to visit him often. And during one of his visits, he gave an idea of quantum information. And it's a note. This is a handwritten note by Charles Bennett. And in the rightmost corner, top corner, you can see it's written false. So it is 1 week. Stephen Weisner told about that. In the next week, there was some error found and he wrote false. But what was the idea? The idea was that you often say that forged currency. So to avoid currency forgery, instead of writing a number on a currency note or a bill, let me put qubits. So qubits cannot be cloned. So qubit is a quantum state, two-level quantum state. And why quantum state cannot be cloned? A lucid logic may be, if you can clone a quantum state, then one copy you can measure position, in another copy you can measure momentum. And then Heisenberg's uncertainty principle is violated. So I mentioned that this is a lucid way of visualizing, but cloning is not allowed. So now if we put qubits on the currency note, so nobody can clone the note. But we are saying that we cannot break RSA or something because of decoherence. So qubits are very fragile, and it's very unlikely that you will be able to put qubits on your currency note and then put the currency note in your wallet, make 4 folds. So even in the lab, it's very difficult. So it's not practical idea. But this has gist of many future research. Much later, there was a conference in Puerto Rico, and Brassard was swimming, and Bennett went to Brassard by swimming, and they did not know, Brassard at least did not know Bennett by face. Maybe he knew the name. And Bennett started telling, you know, my friend has some idea of making this kind of schemes with quantum money. And they started discussing while swimming. By the time they came to the beach, they had the idea of conjugate coding, Weisner pioneering paper with conjugate coding, and they had an idea of conjugate coding based protocol for cryptography. They started sending it. So this has started in 80s, early 1980. First thing appeared in a 1983 IEEE conference in Brazil, but it published only abstract. And they found it very difficult to publish it. So this is from the quotation that shortly thereafter, my good friend Vijay Bhargava, this is written by Brassard. So Brassard is writing about the story of how the protocol appeared. So Vijay Bhargava was a professor in IISc Bangalore. He invited Brassard to give an invited talk in a conference. And Brassard thought that, and there was a possibility that they will publish the full paper. That since it's an invited talk, the review will be quick and it will be easier to publish it. So he's writing, and naturally I choose quantum cryptography considering how difficult it was to get these ideas published in that time. And that led to BB84 protocol, the most famous protocol, and it has an Indian connection because the proceeding was published by, and it was presented in an Indian conference. But now the domain is very big. So we can use the notion of quantum cryptography. The BB84 introduced the notion of unconditional security. I'll come back to that. To areas beyond quantum key distribution. That's the point of this talk. So now we can do for quantum sealed bit auction, quantum and semi-quantum sealed bit auction. We have written several papers. For third world countries or developing countries, it is very important where the corruption is a big issue. So if you can use quantum technology to make the auctions fair, so democracy will be strengthened. So not only that, voting and veto can also be. So we wrote several protocols, but we are not describing them. But I just want to tell you that now CDAC has started something called quantum Q inverse. So in Q inverse is a simulation where you have different test cases has been given. And our protocol on quantum anonymous veto, which we are earlier implemented in IBM quantum computer, is also there. But at the moment, we are not in a situation to do our assembly election or parliament election. But ID Quantic was able to sell for postal ballot kind of things in the Zurich elections, a quantum cryptographic solutions. So there may be a day when people use quantum random number generator to claim that to secure the casino, to claim that in Sikkim state lottery or any other state lottery, if you buy a ticket, there is an equal chance that each ticket owned, because it's completely random, which is satisfied by the quantum random number generator, and somebody can claim that our system. So, but how to do that? So yesterday I spoke with Professor Panigrahi, and he told me that there are many students. So instead of going into deep research, of course I show some papers that what we have done. I just want to give some basic introduction. So we all are familiar with this kind of vector, that a vector A is AI I hat plus A2 J hat plus A3 K hat. What this A2 I hat, J hat, K hat are? They are the unit vector in X, Y, and Z direction. So this is how we write in Cartesian coordinate. Now, to describe a vector, I need this three component, the projections A1, A2, A3. So I can write it in many ways. So I can just write A1, A2, A3. We can write it this way, or we can write it like a column matrix. A1 is the first, A2 is the second, A3 is the third. So A1 is the projection along X, A2 is the projection along Y, A3 is the projection along Z. So then how will you write your basis vectors like unit vectors I hat, J hat, K hat? So since I hat has only one unit projection along X axis, it will become 1, 0, 0. J will become 0, 1, 0. K will become 0, 0, 1. Fine. So this is the notation we'll use. What else we'll use? The whole thing, this is called bracket. You divide it into two pieces. So because of the symmetry, it may appear that my left can become right for your view. But the left hand side is bra, right hand side is Kate. So this is Kate and this is bra. So a bracket is divided into two pieces. Now we write a state A, just the previous vector A, which was A1 I hat. So instead of I hat, now I am writing it like Kate I, Kate J, Kate K, and A is A1, A2, A3. So this Kate I will become just like this 1, 0, 0. Kate J will become 0, 1, 0, 0. It's analogous. Now, if we go for 2 dimension, then instead of n dimension, there will be n such component. In 2 dimension, there will be 2 component. And in 2 dimension, we write 2 basis vectors, just like Kate I and Kate J. Kate 0 is written as 1, 0. A column matrix 1, 0. And Kate 0, 1 is written as 0, 1. So this is my convention. Not only me, maybe other lecturers also have used. And now you can take an inner product. So if you write bra, so bra is a transpose conjugate of Kate. So if you have Kate 0 as 1, 0, since these are real, there is no conjugate, but bra 0 will be a row matrix 1, 0. Now if you are taking an inner product, you just write those matrix 1, 0, 0, 1, and you will see a scalar product, it's a number 1. But if you write them outer product, like the Kate is first and bra is later, then it will be a 2 cross 2 matrix. So here we are showing the outer product. So this inner product and outer product are very interesting for us. So Kate 0, bra 1 plus Kate 1, bra 0, this is this kind of matrix, and this is nothing but a NOT gate. So you can easily think that if it applies on 0, then inner product of 0 with 0 will give 1, and 1 multiplied by Kate 1 will give Kate 1. But in the first term, inner product between 1 and 0 is 0, so this will vanish. So 0 will be mapped to 1, similarly 1 will be mapped to 0, and outer product we can use like a NOT gate. So there are several gates, and here we have shown something, but these are not my interesting for this lecture. Now I want to introduce a product called tensor product. So AB tensor CD, how we do the tensor product? You take an element of the left, it will be multiplied by the entire matrix in the right. So A multiplied by CD, B multiplied by CD, and now you see the size increased. So earlier, each of the qubit can be represented by this 2 cross 1 matrix, but now a 2 qubit system becomes 4 cross 1 matrix. So we already know the matrix for 0 and 1. So if I were to write 0, 1, so this is how I write it. So you see, if you keep on writing, then 1, 1 become 8 cross 1 matrix. N qubit system will be 2 to the power n cross 1 matrix, and the matrix which will be applied on it, the circuitries or a circuit will be, or a gate will become 2 to the power n cross 2 to the power n matrix. And anything with the exponent grows very fast. So with n, it will grow so fast that you will not be able to use a classical system to simulate any quantum system, and that's why you need quantum computer. So I'm not describing this simplifications, but now suppose you have a quantum state with 2 components. So xi AB, but if I can write it like tensor product of, you already learned tensor product, xi A tensor xi B, then If you cannot write, then it is entangled, and if I can write, then it is separable. So 0, 1, suppose you take 0, 0. So this is 0 tensor 0, so this is separable. 1, 0 is 1 tensor 0, it is separable. 0, 0 plus 0, 1 by root 2. So you see, you can take the first 0 as common. So 0 is separable. So first qubit is in state 0. Second qubit is in superposition of 0 and 1. So how we create this entanglement? In my lab, we have a pump beam that follows by crystal called barium beta boron crystal. This creates the process which happens here physically called SPDC, spontaneous parametric down conversion. It leads to two cones. So one cone is horizontal, one cone is vertical, but there are 2 points in which these cones are crossing. So there, if this guy is horizontal, the other one will be vertical. So, but I don't know which one is horizontal, which one is vertical. Then I get a state like HB plus VH by root 2. And you can see that you cannot write like a tensor product of first versus tensor product of second. So any state of 0, 0 plus 1, 1 by root 2 kind of things are entangled. So I need entanglement, and then I need a little bit of quantum mechanics also. So in quantum mechanics, for every physical observable, there is an operator. Operator operates on something called wave functions and satisfies the eigenvalue equation. So it like operator operates on eigenfunction, gives you eigenvalue time the eigenfunction. So our case, this is wave function. F of x will be replaced by xi x, and these eigenvalues are the value which you get in experiment. So for anything which you can do a measurement or which you can measure is a physical observable. For physical observable, you have operator. And if those operators commute with each other, then you can measure them simultaneously with arbitrary accuracy. If not, you cannot. So it is not like that you cannot measure them, you cannot measure them accurately. So that is the case with position in x direction and momentum in x direction, which you popularly know as Heisenberg uncertainty principle. But Heisenberg uncertainty principle is little bigger. Any two observable which don't commute, you cannot measure them simultaneously with arbitrary accuracy. Now I am introducing measurement operator. So measurement operator mi, which projects into the basis state keti, is keti bra. So for 0 it will be ket 0 bra 0. For 1 it will be ket 1 bra 1, and we introduce some states plus and minus. So from polarization perspective, I can think that 0 is the state which is horizontally polarized, 1 is the state which is vertically polarized, plus is a state which is 45-degree polarized. So it has a projection along 0 with half probability, projection along 1 with half probability. So this is 1 by root 2 0 plus 1 by root 2 1, and minus is 1 by root 2 0 minus 1 by root 2 1. So as the talk progresses, it will be more clear. But if we write m0 and m plus, I can see that they don't commute. They are m0 m plus is not equal to m plus m0. So AB is equal to BA means A and B operator commutes. If not, they don't commute. Now, as I mentioned again and again, a qubit is a two-level system. So if you have a proton and you can think that there is an electron, a nucleus and the electron can be either in ground state or excited state. This is a depiction of a bit. Quantum system, it is in superposition. And when you do a measurement, it collapses to one of the possibility in 0 or 1. So if a state is written as ket xi is equal to alpha ket 0 plus beta ket 1, that's a general qubit. If you do a measurement, you will get 0 with mod alpha square probability and 1 with mod beta square probability. Total probability must be 1. So you can create in this way. If you have a single photon source, send it through a beam splitter which partially reflecting. So with certain probability it is reflect, certain probability is transmit. But in quantum world, both happens together. But when you do measurement, then only it collapses to one of them. It's not like that one is going here and the other one is going. Sometimes it's going in transmitted, sometimes it is reflected. It's both reflected and transmitted, and this is the notion of qubit. Now, as I mentioned that if you detect, then it will either be reflected path or in transmitted path. So you just put two detectors. So either this detector will click in the reflected path or the transmitted detector will click. So we have mentioned that transmitted detector gives you 0, reflected detector gives you 1. So if you put two detectors, a single photon source, you have now a very nice device. It's called quantum random number generator. So in the right hand side, we show quantum random number generator. So this is a quantum device. This we have it in our lab, and many labs have this, and it's very easy to visualize. So, but now this collapse on measurement you can check. You can go to a quantum computer, say given by IBM or QAFU, and just write a qubit, put a Hadamard gate, do a measurement, and you see that sometimes it is in 0, sometimes it is in 1. Now we want to first explain a conjugate coding based or the most famous BB84 protocol. So we have already mentioned that plus is 1 by root 2, 0 plus 1 by root 2, 1. So this is the matrix form, minus is this. Now I write explicitly plus plus as the m plus 0, 0, and we show that they don't commute, which I have mentioned already. So what does it mean? You cannot do a measurement in plus minus basis, that is, if you have a polarization, either you have to measure in 45 degree, 135 degree, or you have to measure in 0 degree, 90 degree. You cannot measure in both. So now I start with there are 4 laser diodes, and in front of that I put some polarizers. So this laser diode become horizontal, this become anti-diagonal, this become diagonal, this become vertical, and then we mix them. So ignore AM, PM, AM for the moment, and it goes sent to Bob side. So how the protocol is described? The protocol is described in this way. Alice randomly prepares 0, 1 and plus minus steps, or Alice randomly prepare horizontal, vertical, and 45 degree, 135 degree polarized photons. So this part is showing, left part is showing how it is produced. So you need 4 sources followed by 4 polarizer and some beam splitter to mix them. And you send them to Bob. Now, next step of the protocol says that Bob randomly measured those states in 0, 1 basis or plus minus basis. So the question is, how can Bob do this measurement and how to make it random? So Bob puts a beam splitter. So beam splitter randomly reflect it and transmit it, as we have discussed in context of quantum random number generator. So when it goes in the transmitted side, here is a pink color box that's called polarizing beam splitter. It's an interesting optical element. It allows horizontal light to pass and reflect vertical light. So whenever in the reflected side the detector click, we call that this is definitely vertically polarized, so this is 1. When it goes straight, this is 0. But if the photon is reflected in the left hand side, and here is another circular thing, it's a wave plate. So what is the role of wave plate? It rotates the angle of polarization. So if it is 45 degree, it rotates clockwise for 45 degree and makes it 0. If it is anti-diagonal, it rotates clockwise 45 degree and makes it vertical. The rest of the circuit is same. There is a PBS. So when the direct one clicks or the transmitted one, that means initially the photon was at 45 degree polarized. So this is we know that this is diagonal and the other detector is anti-diagonal. So you see, either this side is work or this side will work, because we have already mentioned either this detector will click or this detector will click. So either we are doing in horizontal vertical polarization measurement or 45 135. So once this has happened, Bob declares that which photon, so photon number 1 is measured in 0, 1 basis, photon number 2 is also measured in 0, 1 basis, photon number 3 is measured in plus minus basis, etc. After knowing the result, but he's not telling the outcome, only the basis. Alice tells that where her basis of preparation matches with the Bob's basis of measurement. So all those cases they keep it. The rest of they drop. So now you see, if you have a state 0 and you measure in a horizontal photon and you measure in this side, it must be horizontal. If you have a vertical photon and you are measuring in this side, it will be vertical. So all those cases the basis match. Quantum mechanics is not probabilistic. Only when a plus step is measured in 0, 1 basis, with half probability it will be 0, half probability it is 1. So unless the basis is wrong, it should match. So now Bob declares half of the result and Alice compares and they calculate that they match or mismatch. So if there is a mismatch, we attribute that mismatch to if. So now you see how if's presence happened. So if there is a if, and if I prepared a state in plus, but if incorrectly choose 0, 1 basis and measure in 0, 1 basis and got 0. So if will prepare 0 and send it to Bob. Now we are telling that Alice and Bob has compared and they are using only those bases in which those cases in which the basis match. So since it's plus, so Bob also measured in plus. But a state 0 can be written as 1 by root 2 plus 1 by root 2 minus. So with half probability it will be plus, but half probability it will be minus. So those half when it will be minus, but ideally every plus sent by Alice should have been plus for Bob. But here is a difference. So how many times the difference will come? So if Bob attacks all of them, half the time that his basis is incorrect and half of those will give incorrect results. So 1/4 of the time E will be detected. This is what makes Alice and quantum cryptography different from classical cryptography. We are not using any computational problem. It's not conditions on anybody's computational power, so it is unconditional. What we are using that if cannot do a measurement in 0, 1 and plus minus randomly, If she does a measurement in plus minus basis, the state collapses to plus or minus. So collapse on measurement, enable the commutation rule or Heisenberg uncertainty principle. We are also using no cloning theorem. If cloning was allowed, Eve should have cloned the state and wait for Bob to declare that which basis he has done measurement, and then in the clone copy, Eve should have done measurement. So the security is coming from no cloning and our inability to measure in the two different bases simultaneously, or inability to distinguish between the non-orthogonal states like 0, 1. 0 and 1 I can distinguish, but I cannot distinguish completely 0 and plus. Okay, deterministic. So there is another protocol called B92, which comes in 92 by Bennett again. So in that case, the first part is same. We are sending 0, 1, plus, minus, but this part is not same. So everything, but after this is same, 0, 1. Sorry. Just a minute. So instead of 0, 1, plus, minus, we are taking a random sequence in this part by choosing only 2. So you take one element from A and D. So either diagonal or anti-diagonal, and you choose one element from H and B. So you block 2 of them. So suppose I am never taking horizontal and I am never taking anti-diagonal. So I am taking plus and 1. So I send this plus and 1, rest is same. Bob does measurement, but you see a plus state can become plus, a plus state can become 0, plus state can become 1, because a plus is 1 by root 2 0 plus 1 by root 2 1. But a plus state can never be detected as minus. Similarly, a state which is sent as 1, it can be plus, minus, or 1, but it can never be detected as 0. So whenever I get 0, so it must be coming from plus, and whenever I get a minus, it must be coming from the 1. So this is how we in B94. So I repeat, in B94 we choose one element from 0, 1 basis and one element from plus minus basis. Say I choose 1 and plus. So when I send, and Bob as before does the random measurement. So if Bob got plus, it can be from 0, it can be from plus. If Bob got minus, it cannot be from plus. Then Bob is sure, if it is minus is often, that it was 0. Similarly, if the plus state is same and 0 state is same, 0 can never give 1. So whenever I get 1, then I know this 1 is coming from plus state. So they keep those cases only, and in 2 bases they can do it, but still we are using conjugate coding. Now, as I mentioned that these are unconditionally secure, but they are not unhackable. This is showing a polarization based attack hacking strategy. So I'm not elaborating it. So Eve is sending a strong pulse, and it's going and it's changing the wavelength of the wavelength. And although we cannot do wavelength of the sources, LD1, LD2, LD3, this is the structure you are already familiar. And by measuring wavelength, I can distinguish which one is what. So we'll skip this. Now, how it is done? So you already know BB84, and this is a satellite-based QKD. So there is a satellite above state 1, and we create a key 1. When the satellite is over key 2, we create a key 2, and then a shared key. Then this satellite declares key 1 XOR key 2. And since station 2 no key 2, he XORs again with key 2 and left with key 1. And then this key 1 is used for communication. So this rest is classical, and then there is no role of the satellite during the communication. So remember the first picture in the slide, the satellite was just sitting. So many countries have satellite, and we are also moving towards satellite. Now I'll tell something interesting. It's called semi-quantum key distribution. So this is very interesting, and it may have many applications because quantum resources are costly, and it is not expected that everybody will have a quantum resource. So you may have a phone which has a limited resource, and bank has the larger quantum resource, and we are doing a secure communication with the bank.
Sir.
So the first step is same, a random creation of 0, 1 and plus minus. Now Bob is classical. Bob can either measure in 0, 1 basis only or reflect it. Bob cannot measure in plus minus basis. Bob cannot produce plus minus basis. So then what happens? Then there are 4 cases. that Alice sent in 01 basis, Bob measure in 01 basis. Alice sent in 01 basis, Bob measures in plus minus basis. Bob sent in plus minus basis. Sorry, Alice sends in plus minus basis and Bob measures in 01 basis. Sorry. So 4 cases are Alice sent in 01 basis, Bob measures in 01 basis. Alice sent in 01 basis, Bob reflect. Alice sent in plus minus basis, Bob measures in 01 basis. Alice sent in plus minus basis, Bob reflect. So all the reflected case, whatever basis was used by Alice to send, Alice does measurement in that basis. If the results match, that means there is no eavesdropping. If there is no eavesdropping, Alice declares when she used 01 basis. So in those cases, Alice's result and Bob's result will match, and since there is no eavesdropping, that will generate key. And all the cases where Alice was sent plus minus basis and Bob did a measurement, they are useless. They are not used anywhere. So this is called semi-quantum. Now I want to go beyond conjugate coding and show a protocol. So you see there is a single photon source, and this thing is called Mach-Zehnder interferometer. Here is a 45-degree polarizer, and what happens if it is a ball-like model? Then 25% of the time this detector would have clicked, 25% of this detector would have been clicked. 50%, but the 50%, or 25%, because you send 100 photon, 50 will go from upper path, 25 will lead here, 25 will reach here, 50 will go from down path. But since we have mentioned that this behaves like a wave, it's present in both paths, so a constructive happens in one detector and destructive interference happen in another detector. So this guy never clicks and this guy clicks 100% of the time. Now, how we use it for cryptography? So these are Mach-Zehnder interferometer based cryptographic schemes, and where conjugate coding is not used. So I'll explain a few, but not D. D is called N09 protocol. It is using Michelson interferometer, but they are orthogonal state based. So conjugate coding is not essential. That's what the message is. And so let's start with this. So we know that if there is nothing, then D1, D2 will click. Now I have a bomb. Bomb is like a detector, and we put in one path. So this bomb, if a photon comes and there is an active bomb, the bomb blasts or the detector clicks. But to know the which path information, particle nice nature, you don't need to put detector in both paths. Putting detector in one path is sufficient, because if it is not clicked, then it must be here. So when you know the trajectory, it becomes particle. It's no more a wave. So if you put a detector here, even the detector is not clicked, the photon is going. That means the photon is going from the upper path, but it's now in a particle nature, and 50% of them will go to D2, 50% of them will go to D1. So now if you use 100 photon, 50 is leading to this detector. If it is an active bomb, it blasts. If it is an inactive bomb, nothing happens, D2 click. But rest of the 50 photon goes here, and mere presence of detector will lead to make it a particle nature, and this detector will click. Half the time this detector will click. So whenever the transmitted side detector clicks, I know that there is an active bomb. I have not sent even a single photon, and I know. Now this is called counterfactual or counterintuitive. Now you see the lower Mach-Zehnder interferometer C. In C, the light is going from the source, and there are two obstacles. One side belongs to Alice, one side belongs to Bob. So if both of them put obstacles, then none of the detector click. If none of them put obstacles, the upper detector click. But when one of them put obstacles, then half of the time the other detector will click. So whenever the other detector click where the mouse is, that means one of them put the detector. But Alice knows whether it is she or if it is not she, then it must be Bob. So same for Bob. So but Eve does not know who has put it. So Eve just knows that it is a successful case.
Am I audible to you?
So Eve's ignorance is 1 bit, but Alice and Bob can pre-decide that if it is Alice's insertion that causes a click, then it will be 0. If it is Bob's insertion of the obstacle that causes a click, then it is 1. So they have a symmetric 0 and 1. Now you look at this B protocol. So B is called Goldenberg-Wedman protocol. So there are beam splitter, a Mach-Zehnder interferometer, and we send orthogonal states. I send a packet Ket A from the upper arm and packet Ket B from the lower arm. But till the time packet A is available in the channel, B is not available because here is a delay. So when B is available, then A is already with Bob. So Alice and Bob can do measurement in A plus B basis and A minus B basis, which are orthogonal, but Eve can do a measurement in AB basis only, A comma B basis. So Eve is restricted to do a measurement in particle-like basis where the trajectory is known either upper path or lower path, but Bob and Alice is preparing in a basis which is superposition basis, and so in this basis quantum state is absolutely distinguishable. So this is a special basis. So by hook and crook I have to make it unavailable to Eve, and it's very difficult because here Eve may also delay, so I must have a very good clock to check that the time of sending plus the time of delay and time required to travel the path must be equal to the receiving time. So a good time synchronization is needed, but we can use something called entanglement swapping. I create several Bell states, and 1 and 2 is entangled, 3 and 4 is entangled, but now I reorient particle order, we change the particle order. If you change the particle order, say 2 and 3 and 1 and 4, and then you see that if choose incorrect basis, suppose I start with that chi minus 1 2 and chi minus 3 4, but then I change the particle sequence 1 2 3 4 ke jagah pe we made 1 3 2 4, so we just change the sequence and then we write again in Bell basis, and then if incorrectly do a measurement on particle 2 3, then particle 1 4 will also be entangled, but particle 1 4 now can be entangled in chi minus, chi plus, anything. So entanglement swapping can lead to a detectable trace, and we have designed many protocols where entanglement swapping is used, and those are orthogonal state-based protocols. So primary message is this talk was that conjugate coding is not needed, and there are tasks which are beyond conjugate coding, and we can go to many things, including initial identity authentication, where Alice and Bob authenticate they're talking to each other. If that's not done, then Eve can cut the channel and tell Alice that I'm Bob and tell Bob that I'm Alice. So earlier in all practical protocols, what is used is a classical authentication scheme. Now we do quantum identity authentication. Here I showcase some papers, but there are many more. So I'll not talk about the voting protocol. My time is already almost over. But I just want to give you a message that there are protocols for quantum voting. And all these things are unconditionally secure, but not unhackable. And there are different kind of attacks: individual attack, coherent attack, collective attack. At the moment in the lab, I can do individual attack only, but I have to show that my protocols are secure against coherent attack and collective attack, because Eve can be more powerful. Eve is Eve is more powerful than Alice and Bob. Alice and Bob is restricted by the major modern technology, but Eve is not. So this may be the future, that someday you may see that there is a line in a bank to open a quantum bank, to open a bank account, and classical bank everybody is closing. And this girl is asking that why it happened, and this guy is telling that, well, yesterday somebody discovered a scalable quantum computer, so RSA is vulnerable now. So RSA is already vulnerable, 22-bit has been broken, but it will be in a stepwise manner. It will not be like a Spielberg movie that some morning you will listen that all the banks have been hacked. So many things to do, and it has problems for everybody. If you are a computer scientist, you have to do the problems. You have a classical electronic guy. There are FPGA boards and such things, and I have started with the engineering challenges. And interesting part is that it often does not require deep knowledge of quantum mechanics or integral to start with or enjoying it. So there are many quantum computers which you can access from your mobile phones too, and there are similar matrix multiplication simulations. So I showcase here some of the papers we have written with this is only a set of papers which we have written with the interns, and interns' names are in red. So these interns all were undergraduate students, and Professor Panigrahi has the legacy to guide maximum number of undergraduate students, and all those who are in touch with him, they know that. So he, me, and the many of the other speakers, for the years we have encouraged the undergraduate students, and this is I'm showcasing that if you have just started, it's possible that you can write in the best journals, papers, and if you just need to give some more time, work hard, and that can, you will enjoy it, and that can also strengthen your future research career. So, but how is the future? So in future, certain things will come. So at the moment, we have single photon superconducting nanowire single photon detector, which we have raised as SNSPD, Quantis, which is the random number generator, Clavis 3 is a cryptographic solution, but we don't have many things. So for example, we don't have a detector which can measure the number of photon without destroying polarization, but tomorrow we can have it because quantum mechanics does not stop it. But certain things will never happen. You will never have cloning machine which can clone unconditional states, and among many other things, we need darkness. So for satellite-based QKD, we are doing in a single photon regime, and we need a dark sky. So Delhi and such places have so much of light pollution. This kind of experiments are very difficult. So we do the exercise, we environment modeling for satellite-based communications, and we see that if we, instead of, so far I was talking about qubit-based analysis, if we go for D level qubit, what will happen? And in my lab, we have implemented up to 145 kilometer of a scheme called cow protocol, coherent one-way protocol, and with the C dot we have done differential phase shift protocol, DPS protocol. So we have some experimental activity, but primarily we are theoretical physicists, and these are some results of the cow protocol, and these are some sources of information. Nielsen Chuang is like our Bible, but there are some simpler sources to start with. So if you are in undergraduate or first year PG, you may start from the books I mentioned in the top, and then eventually you move to Nielsen Chuang. So with this, I will stop, and then I'm open for questions. And if you find that time is short or you are a bit shy to ask the questions at the moment, my phone number and email is more or less public, and it is given in the first slide also. You can drop me a message later also. So I'll stop here. Is there any digital fingerprint technique that can be used in quantum communication so that the... Yes, there are analogous things. Means more or less everything you can talk in classical world, there is a quantum counterpart. So it's there. Means there are quantum digital signature schemes, and even counterfactual quantum digital fingerprint is there. And classically, there is a scheme which there is a theorem which tells that if key is secure, then everything is secure. The encrypted or crypt is secure. So initially, people thought that with QKD and BB84, everything will be secure, but that's not the case, especially with certain things. Bit commitment, oblivious transform, and remote coin tossing in two-party scenario. So in two parties, suppose there are two people who are doing a tossing a coin. So this is a very interesting example. So Alice and Bob were husband and wife. They fought with each other, and they get separated. Now they want to toss a coin and decide who will keep the house. They don't want to see each other, and they don't believe each other friends. So now if Alice tosses the coin and tell that it is head, Bob will tell that my bet was head. If Bob tells that my bet is tail first, then Alice will tell that, oh, head is outcome. So how to solve it? The classical solution is that Alice tosses the coin, puts it in a box, lock the box, keep the key with her, and send the box to Bob. Bob sends the bet, and then after receiving the bet, Alice sends the key. So apparently secure. But you see, whether it's digitally locked or physically locked, you are assuming on Bob's power that Bob cannot break the box immediately and see the bet, see the key. So it is an example of conditional security. So you are putting a condition on power of mathematical power or physical power of Bob. Now, if you want that whether BB84 or QKD will help it, no, because if Alice and Bob make an unconditionally secure key, then Bob already has that access to that key. So in two-party scenario, you cannot do remote coin tossing, oblivious transform, bit commitment. Bit commitment is a similar problem. Alice gives, in morning I tell you that I'll give you this gift, but you will be able to see it in the evening only. So the box is already with you, and till evening you cannot open it. So these problems cannot be solved, but otherwise all the cryptographic problems have quantum analog. Okay, thank you everyone. And if you have any questions, drop me a mail or just a WhatsApp message. Bye. I'm leaving.